Hello everyone, this is Seungho Choi from Chung-Ang University. Today, I will present our work titled FRAMER, Frequency-Aligned Self-Distillation with Adaptive Modulation Leveraging Diffusion Priors for Real-World Image Super-Resolution. This work was done with Jeahun and Professor Jihyong. First, let me briefly introduce the real-world image super-resolution problem. Conventional super-resolution methods usually assume simple synthetic degradations. However, in real-world scenarios, images often contain complex and unknown degradations. Therefore, the goal of real-world image super-resolution is to recover high-resolution images from these degraded inputs. Although diffusion-based methods generate realistic textures, we investigate why recovering high-frequency details is still challenging. We analyze the frequency characteristics of images using the DIP2K dataset. Specifically, we apply a 2D FFT to both high-resolution and low-resolution images and separate the spectrum into low-frequency and high-frequency components. As shown in the figure, high-frequency magnitudes are relatively weak, especially in low-resolution images. In contrast, low-frequency components dominate the overall frequency distribution of natural images. As a result, during diffusion training, the noise prediction loss tends to prioritize these dominant low-frequency components. This leaves high-frequency signals relatively undertrained. Next, we analyze how frequency information is learned across the layers of the diffusion backbone. We decompose feature maps into low-frequency and high-frequency components, and compute the cosine similarity with the final layer feature representation. As shown in the figure, low-frequency features become stable already in the early layers. In contrast, high-frequency features continue to change and are gradually formed only in the final layers. This indicates that gradients in early layers are biased toward low-frequency information, which leads to insufficient optimization of high-frequency components in later layers. Based on these observations, we identify the following problem. Standard diffusion training is dominated by low-frequency signals, which leaves high-frequency components under-optimized. As a result, strong high-frequency representations only emerge in the later layers of the network. To address this issue, we propose FRAMER. Now, let me explain the key idea of our method, FRAMER. This allows us to supervise each frequency band separately. As a result, the model can mitigate the low-frequency dominant training bias and better learn high-frequency representations. Next, I briefly summarize our framework. FRAMER is built on a frequency-aligned self-distillation framework, where the final layer acts as the teacher and intermediate layers act as students. On top of this, we introduce a frequency-aligned contrastive loss. Here, intra-CL stabilizes low frequency features across layers, while inter-CL enhances high-frequency representations. Next, I will explain the contrastive learning component. Next, we analyze the characteristics of low and high-frequency features. In our framework, LF and HF components are distilled using different strategies. As shown in the figure, low-frequency features are highly similar across different samples. This high similarity can increase the risk of false negatives in contrastive learning. In contrast, high-frequency features are less similar across samples and contain richer discriminative details. Based on the previous observation, we designed two different contrastive learning strategies. First, we introduce intra-CL, which enforces consistency within the same image. This encourages stable low-frequency structures across layers, helping the model maintain coherent global information. Second, we introduce inter-CL, which encourages discrimination across different images. This helps enhance high-frequency details by learning richer and more discriminated representations. Next, we introduce two adaptive mechanisms, FAW and FAM, to dynamically adjust the distillation strength. Distillation signals can differ across layers and training stages, which can lead to unstable optimization. To address this issue, we introduce two adaptive mechanisms, FAW and FAM. Next, we analyze the contribution of FAW and FAM through an ablation study. As shown in the table, each component improves performance when applied individually. FAW mainly improves perceptual quality, while FAM also provides consistent gains. When we combine both mechanisms, we achieve the best overall performance across all metrics. Finally, our framework is plug-and-play. FRAMER can be applied on top of existing models without any architectural changes and introduces no additional inference cost. This slide summarizes our pipeline following the training algorithm. During training, FRAMER operates as a self-distillation framework where the final layer acts as the teacher and intermediate layers serve as students. After extracting the teacher and student features, we decompose them into low and high frequency components in the frequency domain. Then, we apply our two key modules, the contrastive objectives to guide frequency-specific learning, and the adaptive distillation mechanisms, FAW and FAM, to dynamically regulate the distillation strength. All losses are finally combined to optimize the model during training. Next, I would like to highlight the inference stage. Since FRAMER operates as a self-distillation framework during training, it does not modify the diffusion architecture and introduces no additional computation during inference. This makes our method plug-and-play and easily applicable to various diffusion models. Also, as shown in the results, our method consistently improves perceptual and reconstruction quality while keeping the training overhead minimal. We also present quantitative results on real-world super-resolution benchmarks. FRAMER consistently improves perceptual quality across datasets and metrics. Importantly, these gains hold across different diffusion backbones, including both UNet and DIT. This shows our method is both effective and robust across architectures. Next, we present qualitative comparisons on real-world images. Compared to recent real ISR methods, FRAMER produces clearer structures and richer textures. Here we show qualitative results on datasets with ground truth. Many competing methods introduce structural distortions or ringing artifacts. In contrast, FRAMER restores sharper edges and more faithful textures, producing results that are closer to the ground truth. To conclude, we propose FRAMER, a frequency-aligned self-distillation framework for real-world image super-resolution. Our method introduces frequency-specific contrastive learning to supervise low and high-frequency components. As a result, FRAMER consistently improves perceptual quality across multiple architectures. Thank you for your attention. If you are interested, please feel free to check our paper or scan the QR code for more details. I would be happy to take any questions.